Hi everyone, welcome to this video. My name is Vincent Gripon. I'm a professor with a French university that is called Télécom Bretagne. And I'm going to present today to you how to solve the Chocolate 2 IEEE-Xtreme problem. So IEEE-Xtreme, if you don't know about it, is a competition that is organized by the IEEE every year. And this challenge was part of the competition this year. It was one of the hardest challenge, as only 5 teams were able to solve it. So, first of all, what is a challenge about? Imagine that you have a chocolate bar that is made of n times d chocolate chunks. In this example, 5 times 3. First of all, I'm going to index all chocolate chunks using pairs of integers like that. And for example, this chocolate chunk has coordinates 3 and 2 because it is line number 3 and column number 2. What I'm going to do is I'm going to eat this chocolate bar, and to do that I'm going to select a chunk. Once I have selected a chunk, I'm going to eat at the same time all chunks with coordinates that are none lesser than the coordinates of this chunk. So all these. Since I did not finish the chocolate bar, I'm going to select a new chunk and do the same, and again, until I select the chunk 1, 1, the last remaining chunk, and I finish eating my chocolate bar. And now the challenge was to find how many different ways to eat a chocolate bar using such a strategy there are, given that the initial size is n times d. So let's take a simple example to understand what happens. Here I have a chocolate bar that is made of 2 times 2 chocolate chunks, which means that I have basically 4 choices to start with. I can select this chunk, in which case I eat the whole bar in one time. I can select this chunk, in which case I eat 2 chunks of chocolate, or this one I eat these 2 and I finish with that. Or I can select the last chunk, in which case I just eat this chunk and I have 3 remaining chunks. Then I have to iterate again and again until I finish eating the whole bar. If you count the number of empties there is in this tree, you will find out there are 10. Now the thing is that if I increase n and d, you will see that the number of solutions increases very, very fast. For example, when n equals d equals 6, the number of solutions is about 10 to the 19, which is enormous. And because of that, we cannot expect to enumerate all possible ways to eat the chocolate bar in order to find the solution. So for those of you that are not familiar with IEEE-Xtreme, the thing was the candidates had to find the solution of the problem in less than a second. So the idea we're going to use in here is we're going to store partial computations. And what I mean by that is each time we make a computation, we're going to store it into memory so that if later on we find the same configuration again, we don't have to compute everything again. We just have to look into memory what was the solution we had then. So the sketch of the algorithm is pretty simple. What it does is the following. It's a recursive function. First, it checks if the configuration we have has already been computed in the past. If that is the case, it returns the corresponding solution. If it's not the case, it counts all possible ways to eat the chocolate bar. That is to say, it looks for every possible chunk to select what is recursively the number of ways to eat this chocolate bar. And once it has finished that, it stores into memory the count associated with this configuration of the chocolate bar. So pretty simple. But in order to be more concrete, I'm going to give the details of the algorithm using the OCaml language, which is a functional language, which is quite nice in order to solve these kind of problems. So first I'm going to define n and d. In this example, I have chosen 9 and 5. I'm going to use the big integer module because I'm going to manipulate very large size integers, and I cannot just use the 64-bit integer that is the native integer of my modern machine. And I'm going to choose a way, and that is very important, of how to represent into memory a configuration of the chocolate bar. And I've chosen this way. So this is an integer array such that it contains as many cells as I have lines into my chocolate bar, and the cell number I contains an integer that is the number of remaining chocolate chunks for this specific line of the chocolate bar. So that's quite simple. That's one way of representing the chocolate bar configuration into memory. There are many others, of course. Now let's speak a bit about how to store into memory. So I'm going to use a hash table, and in this language I have to choose an initial size. So in this example it's 100,000. Why not? I have three functions: one to store, one to retrieve, and one to check if I have already stored the configuration. And because I'm using a recursive algorithm, I have to initialize it. So I'm going to store into my memory the fact that if I have an empty chocolate bar, I have just one way to eat it. Now, last step is I need a function in order to tell me what happens when I eat a chocolate chunk into the bar, how this bar is modified. So this function just does that. It takes a chocolate bar configuration, some coordinates I and j, and it modifies the other coordinates depending on what happens given the problem description. And to finish with, well, I have this recursive function that look very much like the sketch I presented before. So I first check if I already stored my chocolate bar configuration. If that's the case, I retrieve it. If that's not the case, I count and I store it, and I just return the count. And then I have to basically just call my algorithm with the correct parameters. So in this case, the initial configuration is a chocolate bar that is made of n times the chocolate chunks. Well, there was a subtle difficulty into this exercise, and I'm going to explain it right now. The thing is that because of the way I have chosen to represent the configuration into memory, if I have a very small number of lines and a large number of columns, I have a computation time that is reasonable. But if I have the contrary, if I have many lines and a small number of columns, it takes much longer to compute. Of course, these two configurations are symmetric and they should give the same answer, but as you can see, the algorithm is not as efficient in the second case. And the reason for that is here, because here I have a for loop that iterates over the number of lines. So I better have a small number of lines in order for the algorithm to be fast. Well, so basically what I have to do is just change the call of my program in order to make sure that the first argument is a smaller one and the second argument is a larger one. And basically that's all. Thank you for watching this video. I hope you will participate into the next IEEE-Xtreme competition. Bye.